What is the matter? This is the question, right? We're going to ponder on this, the biggest question of all, probably one of the biggest question of all, yeah? What is matter? The matter that makes our bodies, the matter that makes the world, the trees, the sky, everything that is made of atoms. Where do they come from? Where atoms originated? I know they're now recycling in nature, but how did they start it to exist? That is a big question. How? How did it all begin? If there was a big bang and from empty space, from nothingness, everything that exists now evolved, how was that? This is what particle physics is all about. Particle physics is topic 7.3. So this is 7.3 in the IB syllabus. The idea of matter and where it comes from. Okay. So 3 videos to watch, 3 minutes. Each video is 1 minute. You can watch it several times and not get it. That's the idea. The purpose of these videos is to create confusion. But the first one is about how equations are allowing us to, one equation that came from Paul Dirac's mind, Paul Dirac's equation, explains everything, almost everything, except for gravity. Most of the known universe is explained through the standard model. The standard model. So the first video is an introduction to the standard model. I think the second one is the idea of the standard model creating as a consequence the need for matter and antimatter. So if an electron pops out into existence from empty space, there is also the chance that a particle that is made of the same matter but with opposite charge, an anti-electron or a positron, could emerge into existence, and then when they meet, liberate energy. So in a way, these particles and antiparticles are borrowing energy from the universe to create matter and then annihilate matter. And finally, a video on the forces that act in nature. This is probably a complicated analogy. It uses money as an exchange boson to explain the idea of exchange particles. Honestly, I like to visualize the idea of, if it's a rejection between 2 electrons, for instance, I like the idea of them throwing something at them. As easy as that. If an electron throws a ball at another electron, the momentum of the electron changes, the direction of the electron changes as a consequence of you throwing something away. You move backwards, right? And if another electron receives a photon, it bounces away. So the idea of exchange particles are useful to explain the nature of forces. 3 forces of nature make everything. Actually 4. The electromagnetic force, the gravitational force, and then the nuclear force, which is strong and weak nuclear forces. 4 forces in nature, right? So we are getting to a stage where we are able to understand physics at a fundamental level. Another important thing to look at is Chris Donner's videos. Please watch them. He explains what a gas chamber, what a cloud chamber is. Sorry. A cloud chamber. It's a container with a liquid hydrogen probably, or some liquid substance that is at low pressure and easily evaporates. And the traces of radioactivity or the traces of any photon that comes from the sun or any neutrino or muon, any particle that is traveling at the speed of light could leave traces in the bubbles that they make behind them, like a jet plane, leave traces on the air, right? So this is how we look at the interactions of matter or energy and matter in cloud chambers. This is, boom, a particle opening in two, like some kind of collision, some kind of interaction happening here. And these are very short period of times. Interesting video again to watch, 30 minutes, David Butler, explaining the particle dance in a cloud chamber. As if matter is popping out into existence in a cosmic dance because it's being bombarded by rays that come from the cosmos itself. So the father of quantum physics made me, Planck inspired Einstein, and Einstein is the father of the photoelectric effect, the idea of quantum, the idea of an amount of energy that is discrete, quantums of light, photons, this idea, right? Max Planck, just read this. So the light that comes from the flower and the observer, all this is part of a mind, a consciousness manifesting. The union in nature is at the core of quantum electrodynamics, the idea of a unified nature. So these virtual particles, they pop out into existence to exchange forces between them. And this is how we explain the interactions between particles that come from this foam. Okay. Some interesting reading that I strongly recommend is Fritjof Capra. He used the analogy of Shiva dancing, this as a model. After all, quantum physics, you will see, and particle physics, it's about learning a language. So these words, Shiva, that which is not, these words are just metaphors to explain an image of a creation that is creative, that is dancing. Like, for example, matter and antimatter. This idea of matter and antimatter was not inside anybody's head. This idea came as a prediction from this equation here. The idea of matter and antimatter was not inside any human's head, like the idea of quarks. They appeared as a result of a mathematical model that explains nature, right? So Paul Dirac said that the equations that came to his head knew more than he knew, because antimatter was actually detected and measured after it was predicted, like the quarks, same thing. So for instance, a beam of energy, a photon, popping out into or transforming itself instantaneously into two particles of matter and antimatter, electron and positron. And as time goes by, these two particles, probably in a very short period of time, they just, boom, annihilate and create energy. This is what we call an interaction. It's a very important thing. So a vertex is an interaction. Straight lines represent particles of matter, and squiggly lines represent energy or exchange particles or bosons. So these are the rules for Feynman's diagrams that we will study later. Okay? So matter and antimatter. What have we learned from these particles? We know we see these interactions in gas chambers, cloud chambers. We see these interactions and we discover, for example, that a proton is made of 3 quarks, an up, and a down. This is not a fundamental particle. This is made up of quarks, also particles that were predicted by the Standard Model by Murray Gell-Mann in I think in Berkeley or Stanford. I don't know. He predicted this, Murray Gell-Mann, and they actually ended up coming with this solution to the problem that works as a model mathematically. It shows some characteristics. For example, look at the size of the mass. Yeah? The tau compared to an up. So quarks produce hadrons. Hadrons means molecules, particles that are hard, big. For example, the protons and the neutrons. And then the mesons made of 2 quarks. So the hadrons are made of 3 and the mesons are made of 2 quarks. A quark and an antiquark. These are very unstable, right? Mesons lived for a very short period of time. One is a quark of matter, one is a quark of antimatter. And again, these quarks are inseparable. And the other type of particles that we have discovered are the leptons, all the particles that behave like the electrons behave, but the electrons were not alone. I mean, they all have the same charge, the muons, the tau, and the electron, but different masses. And then they come with their associated neutrinos. These are particles that we have observed. Some of them in beta decay radiation. Beta decay, we've observed the electron and the neutrino, sorry, the antineutrino, and the beta plus decay also. Okay, so these are the particles. I don't like this picture. I'm going to redraw it. I'm going to put here this is an electron and this is an electron, and let's say the time is flowing in this direction. Boom. This is the direction of time. So what is happening here? 2 electrons are approaching each other and they repel by exchanging a gluon, a photon. A photon. It's an exchange force, like something has been thrown, so this electron bounces back. There is conservation of momentum. The momentum is constant because there are no external forces acting. So in a way, we are applying the principle of inertia to particles. This is amazing, right? We are saying that there is a constant momentum, therefore the electrons bounce back because this law is conserved, conservation of momentum. Same with the conservation of charge in any interaction.